Dear students, welcome back. In the previous lecture, we had introduced the definition of Laplace transform and we had seen some examples of how to compute Laplace transform and the existence of Laplace transform, what kind of functions admit Laplace transform, and so on. This will be the last lecture of this course. And in this lecture, we are going to continue about Laplace transform. We are going to see other properties of Laplace transform and finally use the Laplace transform to solve ordinary differential equations. So let's start with a property of Laplace transform. Okay, so the Laplace transform is linear. So if you recall what we did in the previous lecture, we had defined the Laplace transform of any function. We defined it as integral from 0 to infinity e power minus px fx dx, right? This is how we had defined Laplace transform. So you can think of f going to L of f. So this Laplace transform can be thought of as a map. We had explained it in the previous lecture. So this map L, which is the Laplace transform, is a linear map. That is, it satisfies this property, right? And the inverse transform is also linear. So the proof is easy. You can do it as an exercise, but still, just for completeness sake, I'll do the part. So if we want to show that it's linear, we need to show that Laplace transform of if I take two functions f1 and f2 and two scalars alpha 1 and alpha 2, then Laplace transform of this linear combination of f1 and f2, if I use this definition here, and we have to replace this f with whatever is here, right? And if we do that, so let's do that. Let me write it again. Okay, so L of alpha 1 plus alpha 2 by definition is 0 to infinity e power minus px alpha 1 f1 plus alpha 2 f2 dx, right? So by the linearity of the integral here, you can actually split this integral as 0 to infinity. You can bring the scalar alpha 1 out. It's e power px f1 of x dx plus 0 infinity, bring the scalar alpha 2 out, e power px f2 of x dx, and this is precisely alpha 1 Laplace transform of f1 plus alpha 2 Laplace transform of f2, which is what is this. Okay, so the linearity is easy to verify. Okay, inverse Laplace transform, we have we are not given the precise definition of it. One can do that. We need to get into the complex domain for that. So let's not worry about it. But that's also linear. Okay, inverse transform is also linear. So the advantage of kind of identifying these properties is that sometimes you can use this property to compute the Laplace transform of some complicated or difficult functions. So let's take this function f, which is sine square ax. Okay, so let's compute the Laplace transform of this f, which is sine square af. So if you use this property of linearity, you can actually easily do from the functions that we have already computed. The Laplace transform of functions which we have already computed. For instance, sine square ax can be written as 1 minus cos 2ax over 2. So the Laplace transform of sine square ax is Laplace transform of this function, right? Because whatever is here is same as this function. Now, because Laplace transform is linear, you can split this, right? So this becomes half times Laplace transform of 1. So the scalar half can come out. So half times Laplace transform of 1 and Laplace transform of cos 2ax. And both of these Laplace transform we have already computed in the previous lecture. Right? So Laplace transform of 1 was 1 over p, and so on. So it's 1 over p, and for cos 2ax is p by p square plus 2a square, which is 4a square. Right? 2a whole square, which is 4a square. And if you simplify this, you get the Laplace transform of sine square ax. So you see, we just very quickly use the linearity property to find the sine square ax instead of using directly from the definition. You can also use directly from the definition if you. This makes the life simpler, right? We have reduced it to some elementary functions for which we know the Laplace transform, and then we are able to compute. So that's one advantage of knowing such properties of Laplace transform. Okay, so Laplace transform is linear. Now another property which is called the first shifting theorem. Okay, what is this theorem tells you that if f is a function such that its Laplace transform exists for p bigger than alpha, then for any given a real number, okay, the Laplace transform of exponential of f, so f is given to you, and what is given to you is that L of f exists. Okay, then what it is saying is that if you know the Laplace transform of f, you can compute the Laplace transform of e power ax f. This product you can compute is what this theorem is telling you, and what it's actually telling you is that this product is nothing but a translation by the a. So whatever is the a that appears here, so the Laplace transform of f multiplied by exponential is nothing but the Laplace transform shifted by the number a which is appearing in the exponential here. Okay, and this is valid for all p greater than alpha plus 1. So this is defined for all p greater than alpha plus a, okay, alpha plus a. So this is the first shifting theorem. So what is this? So basically here it's called shifting theorem because as you can see here, multiplying by exponential is same as shifting the Laplace transform by a. That's why it's called first shifting theorem. Okay, and first because you will also see another shifting theorem after this. Okay, so let's give a proof of this result. So f is given to you for which Laplace transform exists. So you start with Laplace transform of exponential axf, which by definition is this. So e power minus px coming from the definition of the Laplace transform, and this e power ax goes and combines with this exponential. So you have e power minus p minus ax, right? Now this, if you notice, is nothing but the Laplace transform where your p is the new p minus a. Okay, so this is the proof of this result, right? A quick simple proof. So this tells you that if you know the Laplace transform of a function, then the Laplace transform of the function multiplied by exponential is nothing but the Laplace transform shifted by the a which is appearing in the exponent of the exponential. So the advantage of all these knowledge is that, for instance, if your f is the identity function, right, fx equal to x, okay, then you can compute the Laplace transform of e power ax x. Okay, and what is e power ax x? So by this result you know that it is Laplace transform of x p minus a, but Laplace transform x is something which you already computed to be 1 minus p square. So now it's p minus a, so it's 1 minus p a square. Okay, in fact in the previous the previous lecture we had computed Laplace transform of 1. We had also computed Laplace transform of e power ax, if you recall, right? We have done this both in the previous lecture. Notice that e power ax can be thought of as 1 times 1 times e power ax, right? And by this theorem, it will be Laplace transform of 1 times p minus a, but Laplace transform of 1 we already computed to be 1 over p, so this is actually 1 over p minus a, and this is exactly what we computed for e power ax in the previous lecture. So it's also updated. So I've already given you another example as well. Okay, so one more example. We have already computed the previous lecture the Laplace transform of sine. Okay, now let's compute the Laplace transform of sine multiplied by e power x, which by this theorem which we have shown above is Laplace transform of sine where argument is shifted, which by a is p minus a. We already saw that Laplace transform of sine was b by p square minus b square. Now in this case the p is p minus a, so it's p minus a square plus b square. Okay. Now this is the second shifting theorem. Okay, so to state the second shifting theorem, let's introduce the translate of a function. So in this case we are introducing the right translate of a function. So suppose you are given a function f, right? F which is from 0 infinity to r. So basically it's on, so the graph of the function is in the first quadrant here. Okay, so graph of the function is in the first quadrant here, and if you are given some function, let's, for simplicity, let me take, so that you can see it immediately, let's take a constant function, but it could be any function. Okay, so this is your f. So let's say, so what is right translate of f is that you just translate this function to the right side. Okay, that is the right translate of f, which is denoted by tau af. So this a subscript denotes that you are translating. So tau is the Greek letter for t, which is translate. So this a represents the fact that you are translating by a amount. Okay, so a and what you are translating is f, and that's a new function which has an argument f. So after translate, what you get is something like this. If you take the first quadrant here, your a is positive, your domain is positive, so your a is, let's say, somewhere here. So what you are saying is that your function is now this, and so greater than a, it's f, right? And then it's 0 because it was undefined earlier, so you just make it 0. So what you have done is that you have shifted the function f to the right by a amount, right? So whatever is the value, so this you could do for any function, right? You could have done for suppose your function was, say, like suppose your f was like this, right? Then what you would have done here is that your f would be starting from here, right? So that's the kind of, so this is your tau af. Okay, so basically you shift the function to the right side by a. So the value of f, so the value of the shifted function at x is the value of f at x minus a, right? So the value of suppose this is your x, so the value of this tau f at this point x is whatever is the value that you shift by x minus a. So you somewhere here. Okay, this point is your x minus a. Okay, so that is what is called the right translate of f. So using this, we are going to now state the theorem next. That is, if the Laplace transform of f exists, then the Laplace transform of that right translate is nothing but this exponential multiplied to the Laplace transform of f. More or less, if you can think of the second shifting theorem as the as the kind of statement opposite to the first shifting theorem, right? Earlier in the previous first shifting theorem, you saw that the Laplace transform of exponential multiplied by the function is nothing but the translate of the Laplace transform, right? This is again a translate, right? This is the right translate of Laplace transform. What is second shifting theorem tells you? It tells you that the Laplace transform of the right translate is nothing but exponential multiplied by the Laplace transform. Okay, the proof again is kind of quite simple. You just remember that the sign here is minus a. So here you are multiplying by e power minus ap, right? Or in other words, you can think of it like this: e power ap of Laplace transform of the translate is nothing but the Laplace transform of f. Okay, it's like that. Okay, so what is the proof of this result? So let's start with the Laplace transform of the translate function, which by definition is this, because for x less than a the value is 0, so the integral starts from a to infinity and not 0 to infinity, because if you start with 0 to infinity it becomes 0 to a and a to infinity, and in this case the function f is 0, right? So this is by definition. And then if you introduce this variable s is equal to x minus a, then this becomes s, then ds is nothing but dx, so dx is same as ds, and then you have x here, so x is s plus a, and that is what you have here. Okay, and in this case if you look at e power minus pa is something independent of the s variable, so it will come outside the integral here. So what will remain is precisely this. So e power minus apa comes out. What remains is e power minus ps fs ds, which is Laplace transform of f. Okay, so that's the proof of this result. So this is the second shifting theorem. So basically both the shifting theorems are telling you about what happens when you multiply by exponential to the function or to the Laplace transform of the function and so on. Okay, so all these can be, all these properties of Laplace transform can be used to compute the Laplace transform of complicated functions when you want. Okay, if you can see these properties there. Now next is the property, what is the derivative of Laplace transform. In fact, that is one way of looking at it. The other way of looking at it is actually, suppose the Laplace transform of f exists, what is the Laplace transform of the function f multiplied by the polynomial of degree n. So far in the previous shifting theorem what we have seen is what is the Laplace transform when you multiply f by the exponential function. Okay, now you are asking what is the Laplace transform if you multiply f by the polynomial of degree n, and it turns out that the Laplace transform of this is nothing but up to some sign, it is the nth. So if it's an n degree polynomial multiplied to f, n degree, x power n multiplied to f, then it's the nth derivative with respect to the p variable of the Laplace transform. Okay, so that's the derivative of the Laplace transform. So if the Laplace transform exists, then the nth derivative is nothing but the Laplace transform of f multiplied by x power n. So let us look at the proof of this result. So you start, we'll just do it for the case n equal to 1, and you can actually prove by induction to any n. So let's start with the derivative of the Laplace transform of f. Okay, so we start with the Laplace transform of f. This, now you apply the definition of Laplace transform, so it's the derivative with respect to p acting on this integral. This is a derivative with respect to p, whereas this integral is over the x variable, so the p is only appearing here in this so here in this exponential here. Okay, so without worrying about other things, nice thing, we are going to swap this derivatives. So what we have here is the derivative of the p function, which is only this is the only function which is depending on p. So if you differentiate that, you get e power minus px x, minus e power minus px x. Okay, so this is the derivative with this sign, is the derivative of this, which appears here. Now this, if you see, is precisely with the minus sign, which is precisely the Laplace transform of xf. So this is precisely minus Laplace transform of xf, which means if you look at the first derivative is f multiplied by 1 degree polynomial x here. Now you can keep doing this, you can do it for the second derivative, third derivative, so on. That way you can actually prove this result. Okay, so that's a proof of this. So what's the advantage of these properties? Like, you can compute other types of, so you can compute the Laplace transform of some complicated functions, like Laplace transform of x square sine ax. We have individually computed so we have individually computed the Laplace transform of x square already. We have also individually computed sine ax, so on. This is product, and notice that so far we have not we have said Laplace transform is linear, but we have not said that it is multiplicative, right? We don't know, we have not said any property about this. So though we know x square individually, sine ax individually, we don't know what happens to the Laplace transform of product. Okay, so here we are looking at some special cases, really, like when we multiplied by e power ax f, it was a special case where we knew this individually, what happens to the product. Similarly, we know here x square individually, sine ax individually, what happens to the product. Now this theorem tells you that if you are multiplying by, so this is again a special case where the earlier case, so the shifting theorem was giving you about multiplying by exponentials. Here it's multiplying by polynomials. So what is Lx square sine ax? By this result, it is minus 1 power whole square, the second derivative of Laplace transform of sine ax. Now this is something which you already know, the Laplace transform of sine ax. So it is nothing but a over p square minus a square, which is the Laplace transform of sine ax. Minus 1 square is 1, so that is there. Then second derivative with respect to the p variable. So you differentiate this twice with respect to the p variable. If you do that, you get some function, and that is precisely the Laplace transform of x square ax. X square sine ax. Okay, so this is one application of the fact that, if you know the derivative, so if you know the Laplace transform of a function, then what happens to the Laplace transform when it's multiplied by a polynomial of degree n. Right, so see, this result is enough to compute the Laplace transform for if you multiply by any random polynomial, right? That is because you have the linearity, right? So this you can bring in together, so you can use the linearity of Laplace transform. So this is enough to compute. You can actually multiply any polynomial to f and of any degree, then you can compute the Laplace transform using this property, and then the linearity of the Laplace transform. Okay, so all that can be done. So try doing more exercises based on this. I am only showing you some prototype examples. You have to do more examples from the books. Okay. Now, what is the Laplace transform of derivative? So, in the previous setup, what we had done, so this is the derivative of Laplace transform. Okay. What we are asking now is the Laplace transform of derivative. So, if you have a function which is continuous and of exponential order with order alpha, and if the function f prime is piecewise continuous, that is the function f is differentiable and the derivative is piecewise continuous in every closed interval 0a, then you can actually compute the Laplace transform of the derivative of the function, which is given by this formula for all p greater than alpha, where this alpha is the exponential order of f. Okay, more generally, so this is the first derivative. Using this, you can actually compute any kth derivative of f. So the Laplace transform of any kth derivative of f is given by this identity. Okay, so you see here it's like a, so earlier you see in the previous example, the derivative of the Laplace transform was multiplication by a polynomial in x variable. You can see here that the Laplace transform of the derivative is nothing but some polynomial in the p variable. Right? So that's it. So derivatives becomes multiplication by polynomials, translations becomes multiplication by exponentials, and so on. Okay, so this is the theorem. So basically, Laplace transform of derivatives of functions if you know the Laplace transform of the function and all its derivatives up to that point. Okay, so what is the proof of this result? So we have said piecewise continuous, so if you can always separate, you can always write this function as finite number of integrals where in each piece it is continuous, right? So it's enough to show this for continuous f prime. So by definition, L f prime of p is equal to integral 0 to infinity e power minus px f prime of x dx, right? This is by definition. So now what you do, you apply integration by parts to this integral, and that integral becomes this integral, this one, what you have here. Okay, so this is what you get by integration by parts. And here you see, when you go when this x approaches infinity, the term will vanish. So the only term that will remain is when x approaches 0. So when x approaches 0, this becomes 1. So what remains is f of 0 but with a minus sign, and that's the minus f of 0 that you have here. And here it's p times whatever you have here is this integral is precisely the Laplace transform of f, which is what you have here. Okay, so this argument, so this integral is precisely what you have here. I mean, this equality, whatever, this entire thing is here. Okay, now for piecewise continuous, you do the same thing. You just have to split the integral into finite number of integrals and then apply the same integration by parts. It should work. So, and similarly for higher order derivatives, you do the same thing, right? Because you can show it by induction. You have to just can do iteration by parts as many times. Okay, so you are going to get this identity, which will be some polynomial in P. Okay, so as an application, let's give you an example. Suppose, say this is your f, okay, and you want to compute the Laplace transform of this. As I said earlier, we have already computed the Laplace transform of sine and cosine separately, but we have not said anything about the pointwise product, right? So we want to compute the Laplace transform of this f. So one way of doing that is that you can observe that this f is can be seen as the derivative of the function g. So this f can be seen as the derivative of, so if you differentiate this, you get this, right? So this is your G. So Laplace transform of f is nothing but Laplace transform of G prime. But now you already have a formula for Laplace transform of G prime, which is P of Laplace transform of G minus G of 0, right? That's what we have shown in the previous result. So Laplace transform of sine AX is nothing but Laplace transform of G prime, right? And Laplace transform of because this is G prime, right? So if this is G prime, then it is Laplace transform, it's P times Laplace transform of G. So P times Laplace transform of G, so this is your G, which is this, minus G of 0. I don't know, yeah, this is a, this should be G, okay, this is a mistake, okay, this should be G of 0, not F. Now, that's it, but G of 0 is something you know, which is sine 0, which is 0. So you basically have this result, which, because you know what is sine square AX, we have already computed that earlier, right? Using it, we had used the kind of linearity of the Laplace transform to compute the Laplace transform of sine square AX. So in that way, we have this final formula. So that is the Laplace transform of this product. Okay, so that's one application of knowing the Laplace transform of derivatives. There is also another simpler way of doing this just by linearity, is this sine AX cos AX can also be written as sine 2AX over 2. Now you just use the linearity, so the Laplace transform of what you have here is Laplace transform of what you have here, which by linearity is this, so you get the same answer. So alternate method, so you could actually compute the Laplace transform of this just by linearity as well. This is just to show you the application. Okay, so all these are possible ways. So one thing is clear, that we don't know about pointwise, we have not said anything about pointwise product, so we cannot. So for some special class of f or g, we know how to compute the Laplace transform by other means. Okay, for instance, sine square is also seen as product, right? Sine dot sine, right? But we use the linearity of Laplace transform to compute the Laplace transform of this multiplication. Okay, so these properties are required for that kind of functions. Okay, now that we have seen the Laplace transform of derivative, that is f prime, now let us look at what is the Laplace transform of integral. Right, so if f is a continuous function of exponential order with alpha, then the Laplace transform of the integral of f is nothing but the Laplace transform of f over p. Okay, so this is also a kind of expected, because see, if you think, so earlier what did we say, Laplace transform of f was p times Laplace transform of f minus f of 0 and so on, right? So now you can think of, if you think of this integral as a function g, then what you have, f is your g prime, right? So more or less this follows from the previous theorem. Okay, that's the proof of this result actually. So let's set g to be integral of f, which is this. So g of x is this. Automatically you see that by definition g of 0 is 0, right? Because its integral is from 0 to x, so g of 0 is 0. And g is continuous and it's of exponential order. How do we know that? You can verify. Continuity is fine because f is already continuous, right? Now, what about exponential order? You can compute that. Look at mod gx by the integral, which is called the triangle inequality. We know that mod of g, which is mod of this integral, is less than or equal to integral of mod. right? But f is of exponential order with alpha. So this mod f is less than or equal to m e power alpha y, right? And and now if you integrate this, you get m alpha e, so m over alpha e alpha x minus 1. But here m over alpha both are positive quantity, right? So this fraction is also positive. So you are actually subtracting a positive quantity. So this is precisely m alpha e power ax, which basically means that g is of exponential order, where your m is m over alpha now, but it's of same order alpha. Okay, so g is of exponential order of alpha. So which means we can compute the Laplace transform of g, and g prime is f and g of 0 is 0. This we already observed, right? G prime is f. So now what is Laplace transform of g prime? Because that's what you want here. This is g, right? But this f is g prime. So Laplace transform of g prime is p times Laplace transform of g0. This is 0. So this term vanishes, and what remains is just this, right? And g prime is f, so this is lf, which is this p comes here, this p comes here, and l of g is what? L of g is this, which is precisely this. Okay, so we have also seen the Laplace transform of integral. We have also seen Laplace transform of derivatives. Okay, so now the last thing, which is the notion of convolution of functions. So far I have been telling you that when I take pointwise product of functions, we don't know what it is, but there is something else we know, which is a new kind of operation, not pointwise product, which is called convolution, which we are going to define, which are going to denote by star. So this is not pointwise, so this is what is called a convolution operation. This has a nice property, which is Laplace transform of f is Laplace transform of g. So the convolution more comes from there. So if I take two functions f and g, I don't do pointwise product, I do convolution product. Then we will see a theorem that the Laplace transform of the convolution of two functions is the product of the Laplace transform. Okay. So what is convolution? That's the definition. So if you take two piecewise continuous functions f and g, then the convolution of f and g, which is f star g, is defined as integral of ft g x minus t dt. Okay, so this is sum over the pointwise product where one of the function is translated by x, and that is what this x is. So the value of the convolution at the point x is you integrate up to x, and then this g, one of the function, it could be either f or g, is gx minus t. So the first property that you should observe about convolution is that it's commutative. What is commutative? Commutative is this product that, like you know, right? If you a plus b is same as b plus a into b, I mean for real numbers this is true, right? A and b into a. For even for complex numbers this is true. This property is called commutative property. Okay. Like what is like what about matrix multiplication? Is it commutative? Right? So not all binary operations satisfy this property, which is commutative. Right? So, but this convolution operation is commutative. That is, f star is so f star of g is same as g star of f. How do you observe this? Just by simple change of variable. Let's prove it. So let's start with f star of g, which is by definition this. So you start with f star of g, introduce the variable s equal to x minus t. So this is your variable s. So this becomes s. So if this becomes s, t becomes x minus s. So this is your x minus s. But since your t is running from a to x, whenever t runs from a to x, then s will run from x minus a to 0, right? So x minus a to 0, right? And then if this ds is minus dt, so dt when you replace by ds will bring you this minus sign. Okay, so that is what we have. So just by this change of variable we get this. So now you do so here you see x minus a to 0 is same as integrating from x to a, right? Basically I'm adding a both sides, right? Basically this is a property of the integral, right? So this is the integral over this over this interval which is of length a, the same as the integral over this, where you have translated the entire interval by a. So this is minus x x to a, which is same as integrating from a to x, where with minus of x to a is integral of a to x, and this is precisely g star of f of x, right? Because g, whatever comes first, let's say, is f, and whatever comes second comes with translation. Whatever comes first, whatever comes second comes with translation. Sorry. Okay, so that's it. So this is g star of. So we have shown that it is commutative. So we have given the notion of convolution, and we have shown that this convolution operation, so this binary operation is a satisfies the commutativity property. Okay. Now to the main result of the convolution, which is called the convolution theorem, that if you have two functions which is piecewise continuous and on every closed interval, and which is piecewise continuous on every closed interval, so it's piecewise continuous on every closed interval of the form 0a, and it's also of exponential order, which is e power alpha x for any alpha, then the Laplace transform of the convolution of the function is nothing but the pointwise product of the Laplace transform, right? So the Laplace transform of convolution of functions is a pointwise product of the individual Laplace transform. So what is the proof of this? So you start with the Laplace transform of the convolution function, which by definition is this, right? So which by definition, if you recall, is 0 to infinity e power minus px f star g of x dx. But f star gx is given again by this integral 0 to x dt, right? This is f star gx. Okay, so that's just by the definition of the Laplace transform. Now, sorry, Laplace transform and the convolution definition, right? So you have this Laplace transform of f star g is this integral. Now here you have a double integral, right? Now what is the region of integration here? So here if you see, there's a two variable x and t variable. So let me show you. So if I look at the region, so it's positive, so let's look at the positive region. So there is one variable t, so let's say this is the t axis, and let's say this is the x axis, right? So what you do is that you first fix x is running from 0 to infinity, x is coming from here, x is running from 0 to infinity, okay? And since x is running from 0 to infinity, t is also running from 0 to infinity. But the point is, once you fix x in 0 to infinity, once you fix x from 0 to infinity, the t can go from 0 to x, right? So t can go only up to x. So t is less than x once you fix x. So if you draw this line t equal to x, then this double integral is over the region which is this section, this wedge which is here, right? Because this is the region where 0 t is less than x, where t is bigger than 0 and t is less than x, right? So this double integral is done over this wedge here, right? Now what the way, so here you can change the order of the integration, right? Because in this region, so what is, so here what is happening, once you fix x, then you take t up to the x, take t up to the x variable, that's it. So this is your t variable, so you fix, so this you do for every line. So basically when you do this integral, you are doing in this order, you are doing integration along these lines. You are fixing an x, and then first you integrate along t, and then you integrate along the x, right? That's the kind of thing. So you can, so the same region can be seen in the other way as well, right? If I take the same region t equal to x, I could see this in the other way also. I could see this where I fix t, and the integration can be done. So I fix t, so integration can be done from, if I fix t, then the x is from t to infinity, all these lines, let's say these lines. So once I fix t, I integrate over these lines, and then I sum over all these lines, right? So here the way I said, so all so the integration was done along the first you do along the horizontal line, and then you sum over all these horizontal lines. Here I am saying you first do the integration along the vertical lines, and then you sum over all the vertical lines. Okay, so this region and this region are same. It's just that in what order you do is what matters. So here you are doing in what is given here is in this order. So this integral is same as summing this double integral in this order, that is first over the vertical lines and then sum over all vertical lines, right, like this. So what is that integral? That is precisely this integral, where now your t is running from 0 to infinity. So this is your t axis, as I said, this is your x axis. So your t is fixed, your t is running from 0 to infinity, t is fixed, this is your t equal to x line. So once you fix t, once you fix t, then what you do is that you integrate along the x variable from t to infinity, right? So t to infinity is this line. So for each t you get a vertical line like this, and then you sum over all the lines. Okay. Okay, so this is your so this integral and this integral are same because the region of integration is same. You have only changed the order of integration. Okay, so once you have done this, you see that the t variable is here. Then you have t to, so this so here it's 0 to infinity for the t variable, and for the x variable you have t to infinity. Okay, now you introduce a change of variable, which is you call this x minus t as s. So if you call s is x minus t, then what you see is that x is s plus t. So when you have x here, you get s plus t, and then for dt and also dx, dt will not have anything. So dx is what we need to change. So dx, because once you do this, here t is fixed, so dx is ds for fixed t. So this dx becomes ds, so this integral becomes all these becomes this. Now the limits, x is running from t to infinity. So when x is t, s is 0. So s is 0. When x is infinity, s is also infinity. So the limits are from 0 to infinity. Okay. So now you have 0 to infinity, 0 to infinity of this integral. Now here you see there is a sum in the exponential, which is e power minus ps times e power minus pt, but this e power minus pt is independent of the s variable and can come out of this s integral, and it can go here, and that's what we have done here. So this e power minus t, this term will come out here as e power minus t, and what remains is e power minus ps g ds, 0 to infinity, which is the Laplace transform of g. Now that is independent of t, so that will come out. What remains is the Laplace transform of f. So the Laplace transform of the convolution is nothing but the product of the Laplace transform of the individual functions. Okay. So that is one property of this Laplace transform. Now, so you will see applications of this when you do, you can use it to compute the Laplace transform of some complicated functions as well. Anyway, now finally, to finish this lecture and also this course, let's show some applications of Laplace transform on how to solve differential equation, right? That was our original aim, right? Which is why we introduced Laplace transform. Okay, so let's start with an initial value problem. Now this is a first order differential equation, so it's an initial value problem. So because it's first order, you have one initial condition. Okay, so this is a differential equation, you need to solve this, right? So let's solve it using Laplace transform. So what is the idea of, as we mentioned in the previous lecture, the idea of introducing Laplace transform is that the Laplace transform will convert the differential equation into an algebraic equation. Okay, and that is something which you have already seen when we have seen the properties of what is the Laplace transform of derivative, right? Whenever you computed the Laplace transform of derivative, what you got was some polynomial in P, right? So it's natural. So we have already seen the theorem that Laplace transform of derivatives is some polynomial in P. So let's try doing that. So what do we do? This is the ODE. So we apply Laplace transform both sides. So when we apply Laplace transform both sides, what we get is L, and using the linearity of the Laplace transform, what we get is Laplace transform of y prime minus 3 Laplace transform of y minus 4 Laplace transform of this term. Once we apply Laplace transform, we have brought this term here. That's it. So 0 equal, and Laplace transform of 0 is 0. So that's what you have here. So 0 equal to this. Right? Now, what is Laplace transform of y prime? We have already seen a theorem, right? And that is p times Laplace transform of y minus y of 0. Okay? And minus 3 times of Laplace transform is here, and this remains as such. Okay? Now, y of 0 is already given to you. This is the initial value. Okay? So that is given to you, which is 6. And so now what you do, you replace this with 6, and Laplace transform of e power 5x is, you already know, is 1 over p minus 5, and with this 4 it's this, and these two terms are clubbed together because these are the Laplace transform of y term. So it's p minus c Laplace transform of y, and that's equal to 0. So you have something, so which means, now you see this was a differential equation. Once you apply Laplace transform, now it has become an algebraic equation of the Laplace transform of the unknown. So the unknown here is y. Now you have an equation for Ly, and you solve for Ly, which is the Laplace transform of y. And what is Ly? Ly is this, whatever you have. But then our idea is to solve for y, not Ly. So which means we have to go from here to here, which means we have to do an inverse transform. But we have not actually defined what exactly is the inverse transform, right? So the nice way of doing it, at least at our level, is to somehow write whatever we have here as Laplace transform of some function, right? If we write it of Laplace transform of some function, then by linearity we know that y should be same as whatever is here, right? And that's how, and by the uniqueness, and we already talked about the unique continuous inverse of the Laplace transform, right? So, and here we are looking for a solution which is so here we are looking for y as a solution to the differential equation, which means it is differentiable, which means it has to be continuous. Okay, so we are looking for a continuous inverse, right? So how do we write this as Laplace transform of something? So for that, now you see this is some functions of, right, some function in P. So you use the method of partial fractions, write it in terms of individual. So here this remains as such. Use the method of partial fractions to write it as sum of some partial fraction, right? Sum of some fractions. Now this is same as 4p minus 3, 2p minus y. Now you already know what is the function whose Laplace transform of is this, right? What is the function whose Laplace transform is this? You have already seen examples. So this is where it's crucial. Now, I mean, you should know all the Laplace transform of elementary functions by heart. Like, you should remember this, at least for the course, at least till your exam, you should remember this. Okay, we will not, so there will be no table which will be given to you with where you can refer to the Laplace. So at least the elementary functions that we have done in the course and will be doing in the assignments and so on, these functions you should know. So what was the, so this is in the form of 1 over p minus a, right? What was this? What was a function whose Laplace transform was this? So the Laplace transform exponential ax was of this form. So when you say p minus 3, it's more or less for e power 3x, and with a linearity it's 4 e power 3x. Similarly, this one is 2 times e power 5x, right? So it's Laplace transform of 4 times e power 3x and Laplace transform of 2 times e power 5x. Now by linearity you can combine them. So it's Laplace transform of 4ex. So Laplace transform of y is equal to Laplace transform of this, right? So by linearity, Laplace transform of y minus this is 0, and which means y minus whatever is here is equal to 0, which means y is this. So you have solved for y, right? So the solution to this differential equation is this. Okay. Now let's do one more example just to highlight. So this was the first order ODE. Let's just show you a second order ODE just to see the difference there. So you are looking for an unknown function. So sorry, this should be y to r. Okay, I missed that range here. So given y, so we are looking for an unknown. So I don't know why I've said given. So that's also. So you're looking for an unknown y, which is a solution to the, when I say given, I basically mean it's a solution of this initial value problem. Find the y. Okay. So what you do, you apply Laplace transform. So when you apply Laplace transform, you get 0 of L of y prime minus 6Ly prime, Laplace transform on this, and phi of L of y, right? Now you apply the theorem that we know. What is the Laplace transform of the second derivative, right? So Laplace transform of second derivative is precisely these first three terms. P square L of y minus P of y0 minus y prime 0, and then minus 6 of P of Ly minus y0 and 5 times this. Okay, both these are from the result that we have already shown during this lecture. So now y of 0 is 3 given, y prime is 7 is given, so these two values are given, you can substitute them. And similarly y of 0 is given, you can substitute here as well, right? So what remains is only terms depending on the Laplace transform of y. So Laplace transform of y with these coefficients minus 3p plus 11. Okay, so this is what now, which means you have solved for the Laplace transform of y. So L of y is equal to this. So you need to find y. From L of y, you need to go from here to here. So as I said, use some method of partial fractions, split this as something, so on. So you factorize this and then you split it as individual terms, see whether you can write it as Laplace transform of something, use linearity to find y. So I leave it as an exercise, so you can do that. So do it. So these two examples shows to you, how an ordinary differential equation can be easily converted by Laplace transform into an algebraic equation in the Laplace transform various space, and then you solve for that algebraic equation, and then you come back to solve for y. Okay, that's the idea. So with this we stop the lecture and we also end this course. All the best. Bye.